Now, let us study about the chemical properties. Alcohols can be considered to be derived from alkane as well as water. The following reaction shows the formation of alcohol from water. This is easily seen as alcohols have properties in between methane and water. This is a diagrammatic representation of methane and this as water. Now let us see the chemical properties. Methane has a melting point of 89 degrees Kelvin. Similarly, methanol 176.8 Kelvin and water 273 Kelvin. Talking about boiling points, methane has 159 Kelvin followed by methanol 338 Kelvin and water 373 Kelvin. Solubility, which is an important property, methane is generally insoluble in water, methanol soluble in water and slightly soluble in hydrocarbon. Water is insoluble in hydrocarbons. Similar to water forming hydrate with salts, lower alcohols also form addition compounds with salts. For example, let us talk about CaCl2.4C2H5OH, or we can also talk about MgCl2.6CH3OH. In chemical reactions, also alcohols bear striking resemblance to water and alkane. Now, let us see the important properties due to the acidic nature of hydrogen of the OH group. We all know that alcohols are weaker acids than water because of the plus I effect of alkyl groups. Hence, alcohols react only with electropositive metals involving hydrogen. These are the general alkyl groups present, and this is three-dimensional structure of the OH group. Now let us study about the important reactions for the formation of sodium alkoxide and sodium ethoxide. This is nothing but an alcohol reacted with sodium metal to form RONA, also known as sodium alkoxide. And as a byproduct, we obtain half moles of hydrogen. Similarly, taking 2 moles of ethanol with sodium metal results in the formation of sodium ethoxide and hydrogen. The acid strength is in the order of primary greater than secondary greater than tertiary because the releasing effect of the electrons of the alkyl groups. Strongly basic acid substances like organometallic compounds are decomposed by alcohol. For example, ROH plus CH3MgBr gives out ROMgBr and methane. Hence, we can say that alcohols cannot be used as a solvent for Grignard reagent. Alcohols react with acid chlorides and acid anhydrides to form esters. This involves nucleophilic attack by alcohol on the carbonyl carbon. The leaving groups are Cl- or CH3COO-. We can see that this is an acid anhydride and this is a carbonyl compound. In this carbonyl compound, the C here is known as carbonyl carbon and this as carbonyl oxygen. Now, let us see the reactions in which the OH group is involved. The following reaction, ROH is nothing but an alcohol. Here, the OH group attacks this carbon and replaces the chlorine, followed by in which we will obtain the product ROHCOR- and the chlorine ion. Further on hydrogenation, we obtain ROCOR-. In the secondary reaction, where we have an alcohol with ketone, we obtain the following product ROHCOR- along with carboxylic ion, which on further hydrogenation we obtain the H+ ion along with the ketone product. Generally, carboxylic acids react with alcohols in the presence of concentrated sulfuric acid or nitric acids. Alcohol molecule brings forth a nucleophilic attack on the carbonyl compound to form esters. In the given example here, alcohol reacts with this carboxylic acid, and further on hydrogenation we obtain this ester along with water molecule. Similarly, ethanol on reaction with acetic acid in the presence of H+ ion, we obtain ethyl acetate, as we can see here, along with H2O molecule. This reaction involves the protonation of the alcohol followed by nucleophilic attack by chloride ion. Protonation weakens the CO bond considerably. The removal of H2O molecule from the protonated species is facilitated by the anhydrous zinc chloride, which is also called ZnCl2. Reactivity for this reaction with respect to alcohols is like as follows: tertiary greater than secondary greater than primary. This reaction is generally used in the Lucas test. Now let us take a tertiary alcohol. When reacted in the presence of concentrated hydrochloric acid in the presence of anhydric ZnCl2, we obtain CH3 thrice CCl and water. Here, turbidity appears immediately at room temperature on the occurrence of the reaction. Now, if we take a secondary alcohol in the same conditions and anhydrous ZnCl2, we get the turbidity after 5 to 10 minutes with the same product. On reaction of a primary alcohol under concentrated hydrochloric acid and anhydrous ZnCl2, we obtain the same product, but no turbidity appears at all. But we will obtain the turbidity only on heating. Similarly, alcohols are converted to alkyl chlorides by thionyl chloride in the presence of pyridine. Alcohol, that is RCH2OH, on reaction with thionyl chloride, which is also known as SOCl2, in the presence of pyridine, will obtain the product RCH2Cl plus SO2 plus hydrochloric acid. This hydrochloric acid here can be removed by pyridine, and sulfur dioxide, being a gas, escapes. Hence, there is no separation problem in this method. This reaction involves the formation of alkyl chlorosulfide as an intermediate. If you see this following reaction here, this alcohol on reaction with alkyl chlorosulfide will be obtaining RCH2O SOCl. An intramolecular nucleophilic attack by the chlorine in the intermediate on the carbonyl carbon atom results in the removal of sulfur dioxide, forming alkyl chloride with retention of configuration. That is expressed in the form of equation here. RCH2O SOCl on decomposition gives RCH2Cl plus sulfuric acid. This reaction belongs to SN1 mechanism, which is a nucleophilic substitution internal. And furthermore, alcohols are converted to their halides by the action of phosphorus halides. The alcohol here, ROH, on reaction with PCl5 will obtain the product RCl plus POCl3 along with hydrochloric acid as a side product. Similarly, 3 moles of ethanol on reaction with PCl3 will obtain 3 moles of C2H5Cl along with H3PO3, which is also an acid. Similarly, alkyl bromide by phosphorus and bromine, alkyl iodide by phosphorus and iodine can be made. In all these cases, an intermediate is formed, which undergoes nucleophilic displacement reaction with halide ion. In the following reaction here, RCH2OH reacts with PCl5 to form RCH2OH, PCl4 and a chloride ion. This is how it attacks the oxygen ion here. The carbon here is the primary carbon, and this O replaces, and we obtain the product RCH2Cl POCl3 and hydrochloric acid. Now let us study about dehydration. Alcohols undergo intermolecular dehydration by treating with concentrated sulfuric acid to give ethers. In the first step, alkyl hydrogen sulfate is formed, which with excess alcohols undergoes nucleophilic substitution. This is a three-dimensional structure of hydrogen sulfate, and this represents sulfuric acid. And we know that ROR- is a general form of ether. Now let us see about the intramolecular dehydration. This takes place leading to the formation of olefins. This reaction involves in beta elimination. It is an elimination of order 1 and the intermediate is a carbonium ion. If we can see here, this is a tertiary alcohol. On hydrogenation, we obtain a carbonium intermediate and water. This carbonium intermediate on further reaction will form the result of alkene and H+ ion. This follows an E2 mechanism if the ethyl hydrogen sulfate is involved as shown. This reactant on further decomposition will obtain the formation of ethene and H2SO4. Thus, ethyl alcohol gives ethylene on treating with excess concentrated H2SO4 at 440 Kelvin. Dehydration can also be carried out by passing the alcohol vapor over alumina at 620 Kelvin. That is depicted as a reaction here. Alcohols react with ammonia in the presence of heated alumina or thoria catalyst at 633 Kelvin to form a mixture of amines. Amines are nothing but NH2s. Here, ROH reacts with ammonia at 633 Kelvin in the presence of Al2O3, the formation of amines. On further addition of alcohol, we obtain R2NH, which is a secondary form of amine, and on further addition of alcohol, we obtain a tertiary product of amine. Heated alumina removes the water completely here.